Our next speaker is Professor Scott Kirkpatrick. He has had quite a long career in IBM's research division, and some of the work you may know him by is the work he's done on percolation theory, on spin glasses, and optimization, simulated annealing, and so on. I think his name is very well known in all those fields. Now, in 2000, he retired from IBM and is now professor of computer science and computer engineering at the Hebrew University. Now, the other thing that I need to point out is that he is also an Exystence member. And in that context, he has won an award. It's a project called Avogadro. It's an integrated project, and he described it as a half executive. Half of the executive on the Avogadro integration project. Now, that project is measuring the edges of the web. That's in the internet, and that is very much what he will talk to you about. So overall, both in his career in IBM and now at the university, he has been working with complex systems theory all his life. And his talk today will be from scale-free web to Avogadro-scale engineering. Thank you, Scott.
Well, it's nice not to be the first speaker because a number of interesting themes were introduced by Lord May and that I won't have to, that I can simply assume everyone understands by reference. I very much liked his framework of the Tycho Brahe, Kepler, Newton stages of understanding of a phenomenon. But I actually disagree with him. He had the feeling that we don't have any Newtons anymore and that little was going on at the foundations. I think, in fact, one of the things I'm going to talk, or several of the things I'm going to talk about, while there may not be any Newtons among us anymore, we're doing our best to try to find what are the foundational ideas about how complex models can be analyzed, how predictions can be founded more soundly in very large and very random systems. And I will talk about that. So, for example, if you, good, this is working. If you take the internet, which is not quite focused, there's at least 1 million more nodes that will come into focus, deep in the universe. But I don't think there's anybody back there. So let's not worry about that. The print's readable. If you take the internet, the data gathering stage of discovering that its statistics had little to do with random graphs as they had been thought about for 20 years, the Brahe stage, that goes back a ways to the discovery of exponents. The analytical framework, the Kepler framework of looking for patterns without asking where the patterns came from is pretty much that of casting the degree distribution in the internet into a log-log plot or a semi-log plot and discovering power law distributions of the connectivity of stuff at various levels in the internet. And a very important step in understanding how this comes about are the papers by Barabasi and collaborators, and now quite a few people have hopped into that, whose underlying observation is that long-scale phenomena that repeat themselves over many scales, are a natural consequence of things that grow and that have what they would call let's see, don't have the right phrase in front of me. But anyway, networks that grow with a preference for joining the existing network rather than each piece that is merged into a network having characteristics of its own that are a little affected by joining the network. When you put together a lot of stuff that is not very affected by its neighbors, you get a distribution that's characteristic of the raw material. When you build things in an aggregating way, and the pattern at any one point has a strong influence on what comes next, you get phenomena that transform down to smaller and smaller scales. And I think that, while that's not the Newtonian theory of gravity, that understanding is behind a lot of the work that's going on today to understand very large networks that are continually growing, so that there is no point at which you can look at it as a whole. So things I'll talk about are, I'll focus my interest on information networks. But there are many kinds of information. The project that was alluded to, Evergrow, is focusing principally on the physical internet and to a lesser extent on the content of information, the web of information in the internet. The physical internet today has at least 1 billion hosts, a comparable number of routers, the elementary points at which packet paths branch. Autonomous systems, ASs, are the next level of hierarchy. There's at least 10,000 of them today. They actually appear and disappear, and the number grows far slower than the actual content of the internet. But everything is changing. The time scale of presence of a specific host may be minutes. The time scale of registration of long-term existence of hosts is days. And when you look at information on the web, which is several orders of magnitude, of which there is several orders of magnitude more stuff if you count it by the character or byte, but about the same amount of stuff if you take the point of view that 10 to the 4th bytes, 10 kilobytes, is approximately a web page. So again, we're talking about 1 billion things. That is linked in a much longer range way and has an even stronger scale-free characteristic when analyzed, when you put on your Kepler hat and look at power law characterizations of the content on the web. The newest, well actually no, it's actually genetic expression data from gene chips and from the awesome rate of automation in molecular biology experiments is also operating with about 10 to the 9th things. The human genome is of scale about that. Each of these present enormous problems of interpretation if we want to, number one, understand what's going on. In the case of genetic expression data, you'd like to have tools that would go beyond the Kepler stage of finding patterns, finding groupings, to the Newton stage of finding medicines and getting rich. Newton was not opposed to getting rich. So this is, in fact, a very active process going through to all 3 stages of analysis. The tool in genetic expression, which I'm not going to talk about today, but I'll just mention it for its interest, is inference networks, Bayes networks. And I will talk about a technique that's a little bit older that appears to underlie the recent remarkable successes of these inference networks in fitting together this kind of information. And those are survey propagation and belief propagation, which I'll speak about in a few minutes. And they are techniques which I believe go beyond just finding patterns and give us a sense of how to accurately create side information locally and in a distributed way about what is going on in complex networks. So that's what I want to get to. I also, in the course of the talk, want to point out that up to this stage of 10 to the 6th to 10 to the 9th objects, the techniques that have been most successful are techniques for solving well-defined fixed problems, for finding optima. If you're a mathematician, you always want to find a global optimum, even if it's 1 part in 10 to the 6th better than a very large number of almost global optima. If you're an engineer, you want to know whether there is or isn't a solution better than a threshold of acceptability. You want to find that as soon as possible, and once you've found it, you'll go make one. Either way, we know how to characterize a problem and solve a problem in very large scale systems on the scale up to about the billion that we're currently reaching in large information networks. We know how to optimize the layout and predict accurately the performance of microprocessors and large systems on a chip. We know how to send an army into a strange country and get most of the soldiers back and have most of the weapons arrive where they're supposed to, and to plan for all that. The new ingredient, or perhaps being faced here as well, is the dynamism of the networked information problems that people are trying to solve. To oversimplify it, I think what's happening is an optimization problem is becoming a problem of control, of management of a changing situation, where the objective is not to find the best of something, but to provide corrective information and directional information so that the system under management or under control stays in a proper or an optimal piece of its phase space. So what I'll talk about are new methods for optimal design on the scales of 1 billion or so, and how dynamics changes them. So first of all, what's happening in engineering of these systems as they become more dynamic is that they're essentially open. Physical methods such as modeling the circuits on a chip as if they were atoms and had springs between them. I'll give you a classic physical method. It's called simulated annealing. If you want to create a design of where to put 1 billion circuits in a microprocessor, you start with a list of what those circuits are and how they're connected to each other, which ones drive which other ones. You think of them as little springs. If the system is to run fast, everything has to be close to what drives it and not run long wires across the chip. However, if the chip is to run cool, and if there's enough space left for the wires, you have to pull things apart and leave room for the wires to go in between and keep the hotter things apart from each other. So there's a fundamental frustration between these two objectives. One can write down a cost function, which is like the energy of a system of atoms, with springs and other forces that reflect the costs of pushing them too close together, and try to solve by some sort of a Monte Carlo or Metropolis-style simulation for the best ways for those atoms to lie down. This is an engineering problem, so as soon as you find an arrangement of the atoms that is good enough, you stop and you make the chip. And it works. It's widely practiced. The trick that comes from physics that makes it all possible is to throw in a simulated temperature, which is like sloshing things around with a little bit of extra energy from outside. So physical methods like that, modeling things as atoms with forces representing through a sort of shortcut the complicated interactions that you know you have to deal with, the complicated trade-offs that you have to deal with, is a powerful technique for dealing with these systems in which there is no easily recognized best solution, many compromises, and the trick is to discover whether any of the good compromises is good enough to proceed with an engineering process. Those methods are being opened up in a surprising number of ways by going away from the physical background, which means we have fewer proofs of whether they're going to work, but we often have ways of improving the optimization methods. And I'll talk about how game theory has totally broken the physical analogies, but I'll get to that in a moment. Systems properties are often characterizable at extremes of the parameter space. We know that if we put all the circuits in my microprocessor chip right in the center, that the springs will be totally relaxed and that piece of the objective function will be perfectly satisfied. But it won't wire because there won't be a possible, it'll be all too hot. So there's a characterization of the solutions or a characterization of the problems if we're looking at a class of problems as occurs in logistics, the airline example from the previous chart. What one often finds in dealing not with problems which are very individual, like designing a microprocessor, but problems which come in families, is that they have a parameter space. If you talk about logistics problems, there's the size of the problem, the number of aircraft in the airline. There's the connectivity. There's the extent to which things have to connect to one another. Or in many logistics problems, the connections are through constraints which couple the variables. A constraint, there was discussion earlier about how you have a layer, you have layers which link together, layers of where the stores are and layers of customers in their cars being unable to get from one place to another. You know, constraints in effect are a layer. You have assets and you have a layer which by constraining what the things on the lower layer can do, link them together. Generally, if the influence of the constraints is very slight, these problems, the problem of designing a strategy, for example, for everybody getting to work, is very small if you have lots of highways and lots of cars. On the other hand, if you have only one bus and they've all got to go on it, that's the other end of the parameter space. It's obvious that it's going to take a long time for everybody to get to work. So the physical insight that is behind this particular piece of rambling is that very often we look at a family of problems, different ways of getting everybody to work depending on whether they all have cars or they all have to go on the bus, has two extremes that we can characterize. One of them is easily solved. The answer is yes, everybody gets to work on time. The opposite is very difficult to solve. Or clearly, and perhaps the answer to the first question is no, they're not going to get to work on time. Let's see how long it's going to take them to get there. In between, if you're used to thinking of these things as physical models, something dramatic probably has to happen because an answer was yes at one extreme and no at the other extreme. And the question is, are we going to go through a wide range of the answer being sometimes yes and sometimes no, or is it going to change dramatically from yes to no at some value of the parameter in between? Now, in simple systems that are studied in physics, like, say, liquids and gases, there are usually values of pressure at which the gas begins to liquefy, or either through forming droplets of liquid, values of temperature, pressure, and other parameters. So you go from the answer being gas to the answer being liquid through a phase transition. That's an example of Avogadro's scale. Avogadro's number, roughly 10 to the 21st, is the number of molecules it takes to make an amount of a substance whose weight in grams number, the number of neutrons and protons in the molecule. So when you have Avogadro's number worth of stuff, any of these issues that go from yes to no with a continuous change of a parameter must do something dramatic in between. The answer is not maybe over a wide range, but almost certainly yes, going to, almost certainly no. And in that vicinity where it's hard to know whether the answer is going to be yes or no, this kind of physical argument shows you that phase boundaries are where it's hard to tell the right approach to solving the problem. So algorithms for managing large complex systems, if they have phase changes, answers that go from yes to no, are hard in those regimes. And very often, those are the regimes we're most interested in. Because we generally apply automatic methods of planning and automatic methods of control in order to push our ability to manage large systems right up to where they become hard to manage. So I'm going to not go into some of the details up there. In particular, there are now theorems that give us some confidence, although not a complete answer, to the extrapolation from physical behavior with phase transitions to the behavior of large combinatoric systems that go from yes to no across a parameter space. And the statement is, asymptotically, there is, one expects, under rather simple situations, rather simple criteria, to have a sharp transition between one kind of behavior and the other. And correlated with this kind of sharp transition in the overall structure of the system, the approach that you would take, is difficulty for almost all algorithms that we can think of to manage such systems. Now, what I want to talk about next is a set of techniques which have been tested in a classic problem in logistics, satisfiability, and its simplified or toy model 3-SAT, which I'll describe to you with my hands, that works extremely close to, these are a set of randomized techniques that work extremely close to a well-characterized phase transition, and are my basis for thinking we can take these ideas and generalize them to a wider class of very large random systems. Let's see, I haven't used any space to define equations here, so let me say in words what is satisfiability. If you want to characterize a logistics problem, which could be something as simple as making sure that airplanes and crews and food and spare parts all get to their destinations at the right time, you can generally write you have a bunch of variables which are airplanes and their location and other things that go on the airplanes. You have a bunch of logical statements which I'll call clauses, because that's the term generally used, and each of the constraints on this system is some short statement that a couple of things have to be true. That's one clause. And the health of the system is the sum, in effect, the logical and of all the clauses, all the constraints that have to be true. So you can write that down in what's called conjunctive normal form, that a formula, the problem I'm trying to solve, is a huge long string of these little clauses. And ideally, all of the clauses must be satisfied in a successful solution. So it's the and of a bunch of clauses. The cleanest way to write the clauses is as an or. You take a couple of measurements of statements about this whole system, about some little piece of the whole system. And the requirement of the clause is that at least one of those statements has to be true. So 3-SAT is a particular way of constructing these things that's amenable to mathematical study, in which we have a whole bunch of Boolean variables, state variables, n of them, and we have a large set of clauses which are boiled down to, reduced to groups of 3. And what makes it an analyzable model is, without any proof that this is really, that we haven't thrown out the particular problem we were first thinking about, we create a generalized problem, or a family of problems, in which every clause involves 3 of the Boolean variables selected at random, 3 different ones, and each of them has half a chance of being required to be true and half a chance of being required to be false. Now, what makes it tricky is there may be, if I've just required that x, y, and z, at least one of them be true, there might be a clause somewhere else that asks that x be false. There might be a clause somewhere else that asks that y be false, and so on. And so m, the number of clauses, is the source of our difficulty. And for m very small, this problem is easy if we have a lot of variables in the limit where m and n are both large numbers. For m extremely large, we're going to have situations where basically the truth of x by a chain of other clauses implies the falsity of x, and therefore there's no solution, and one has to start looking for approximate solutions in which some minimal number of constraints are violated. And this becomes a fairly rich and interesting mathematical challenge, and we'll try to extract some lessons from it. The phase transition in the simplified 3-SAT model occurs a little bit above 4 clauses per variable. And I won't go into it in detail, but the powerful tools that have been thrown at the problem have given us a lot of insight into exactly how the phase change comes about. And the insights extend to discovering that the variables come in, that the solutions come in groups, and there's a clustering that forms of solutions. From one solution, you can find nearby solutions, but not all. And obviously, if the clusters are small and highly separated, it's a problem of a different nature than when the clusters are large and few, and you can move relatively easily from one solution to something else that a subsidiary measurement shows is preferable. So we've learned a lot from studying this problem about the relative ease of solving problems that are fairly hard, and how hard to work in solving the hardest problems, and where there are gains and where there appear to be no gains other than changing the definition of the problem. I got interested in this model about 10 years ago working with Bart Selman at Cornell. He was at Bell Labs then. We were studying this model. We were studying 3-SAT using the best algorithmic tools available at that time, which were powerful search techniques, exact search techniques that could exhaustively assign values to variables and backtrack if a conflict was found and then keep plugging forward. These had the property that eventually you found a solution, but sometimes you had to back up and start over a lot of times. So they were kind of slow. And they could also very efficiently prove there was no solution if you backed up to where you began. You had exhaustively explored a piece of the phase space, and you had by that process proved that there was no assignment of the subset of variables touched in your search that would satisfy the overall formula. So these were powerful techniques. They were also expensive. We were able to solve problems of approximately 300 variables and 1,200 constraints, and characterize them statistically to show that all the characteristics of a phase transition, critical ranges, power laws, critical ranges of fluctuations, finite size scaling. For those of you who know what that is, it's a powerful tool for recognizing the power of fluctuations to give you evidence for the phase transition in finite size systems away from the point where the change actually occurs. The spreading of these phenomena as systems get smaller is something that we know how to predict. We were able to show all this using the best tools of the early 90s. The methods that have now come along have pushed the boundary from 300. Faster computers might have gotten us, since these are exponentially hard problems, another factor of the log of 10. But we're now routinely solving problems of order 10 to the 7th, 10 to the 8th, and getting good statistics on problems with 1 million variables. And the answer is a heuristic method that uses distributed computation and softens. I can only point at the lower half of the screen, but fortunately, the general method that emerges from survey propagation and belief propagation, which I'll define next, is that they take a hard problem of Boolean variables. A variable can either be, a spin can be up or down in the magnetic language. A airplane can either be present at a particular airport or absent at the particular airport. And they replace it with probabilities, the probability that the airplane will get to that airport. And they use them to collect in a softer way reasonable local assertions that you can then build solutions out of. And this appears to be a powerful technique and a generalizable one. There's also an increasing willingness in this large problem to use random techniques. In other words, you can either soften the Boolean variables, which are hard. If you remember integer programming is really hard. Continuous programming is easy, and sometimes the solution to an integer program can be found close to the solution to the continuous program that approximates it. Well, something like that happens in the softening set of tricks for very large problems. A second way to deal with discrete variables in hard optimization problems is to simply use random walks, to search around quite broadly in the space of these variables. There's a powerful tool that is applied to the 3-sat problem, which is basically to take a random walk in the space of the variables, choosing the variables to flip in a clever way, but then having been clever about where to apply corrections, the technique, it's called walk-sat, the technique then is quite blind, intentionally so, in looking about, and has only a sort of a soft overall control that keeps it moving towards a possibly better solution. Nonetheless, it works really well. The traditional exact methods have a cost which is exponential in n. The cost of a random walk is linear in n when it works. And the way you see that is I've plotted 3 sizes of samples. The green spots are data at various values of the ratio of clauses to variables in 3-sat. The blue spots, which are more confined, what I'm plotting here is the number of random walk steps needed to find an answer. And there's a lot of variability, but the curves get tighter as the systems get bigger, which is a classic physical behavior. And they are linear. That is, the cost per spin to find a solution is a single function with variations about it of the difficulty of the problem until you reach the point where it becomes hard to solve essentially all problems. And this is the point where the simple linear methods break down. Cleverness over the last few years has essentially moved the point of that breakdown from down here, away from the phase transition, to where it's very close to the phase transition, but not all the way there. So this range, if it's important for engineering, requires more powerful methods. Those methods are a technique of constructing, as I said, soft local estimators of what the variables are going to do. The most powerful one that I used in constructing this chart is called survey propagation, and it only works in this very hard regime, and it works by making a very novel sort of assertion. The typical way to soften a problem with a binary variable is to take as your soft variable the probability that the answer is going to be 1, which is 1 minus the probability that the answer is going to be 0. And there are ways of calculating with that. That's a long-standing tradition in artificial intelligence called belief propagation. A slight variation on that is the insight that comes from a longer and more complicated route, that in fact the variables fall into several classes. The classes are those which are always 1 in a particular group of solutions. So my statement is going to be local to a cluster of solutions. So you first have to have some reason to believe that solutions break into clusters of like assignments. Within a cluster you find, or you might find, variables which are always 1, variables which are always 0. So if you set one of them correct for that cluster and another one wrong, you're stuck with a conflict. You're never going to get a good solution. And variables which can be either within the group of good solutions that characterize one of these clusters. Survey propagation is a technique for separating the variables into these 3 classes. And now the class of variables, so you have settled yourself into a space with some subset of the possible solutions to the problem within reach. The class of variables which are certain to be 1 can be identified by these techniques, and decimation scheme is a sort of a partial substitution. Instead of the complicated methods that I used 10 years ago to search by asserting the values of each variable one after another and backing up when a mistake is discovered, these techniques simply assert the value of variables which have been found by the softer methods to be almost certainly 1 or almost certainly 0, perhaps relative to a group of solutions. And the result is you're able to transform the formula to something simpler, which in effect moves it out here to where the random walk method can solve the problem. because after a while, the survey propagation method stops and says, I've found all the clearly assigned variables that I can tell you about. The rest are sometimes up, sometimes down. Why don't you go ask my friend the random walk to help you find any of the resulting solutions? The method works. And I believe it's generalizable. I'm involved in some projects to tackle other problems by this class of methods. The basic technique, somebody asked about renormalization group. In effect, this is a series of transformations which has much in common with the renormalization group, transforming to a simpler set of variables than the original problem. In this case, it is transforming based on an insight that some of the variables have a clear role and others have multiple roles. So it's different from the change of scale that is envisioned in the classic renormalization group that's used in physics. But it is nonetheless a systematic transformation from a hard part of the problem space to an easier part of the problem space. And I think that's the source of its power. Well, I described surveys and beliefs. What I've called surveys are these beliefs in a slightly richer space based on some assumptions about the nature of the solutions, that they have to be clustered and you have to distinguish the things that can be done at this time from the things which should be saved for later. Some really interesting work that's at the moment not published, but I'm involved in. There's a group under Ricardo Zecchina in Trieste that's working on this. Suggests that you can mix the approaches. You can actually come up with transformation equations, like the sort of renormalization group that I alluded to, which are a linear combination of the belief propagation way of the equations for constructing beliefs and the equations for constructing the more complicated surveys. And these turn out to have properties that, if used carefully, give you the best of both worlds. The surveys tell you some very subtle things about the solutions to these problems in their hardest regimes, where solutions are clustered together. The beliefs are true across a wider range of problems. They are a powerful way of getting information about the easier problems. You mix the two and you get a transformation that works like the belief propagation, but in the harder regime. And so an open question is whether the path that we have taken to find this method of surveys, which seems powerful in one kind of special problem, can be generalized to a wide range of problems in logistics and artificial intelligence through the simple process of generalizing the equations that we work with. So I've told you that soft methods and building on speculations about the basic role that the different variables have and the understanding that some things are more constrained than others is a powerful general technique. There's one other technique that comes from physics that I think we'll see getting more widespread use, and that's the notion of a cavity. These problems are too large to solve by inverting a matrix, by writing all the interactions down and saying, well, AX equals Y, we know Y, we know A, let's find X by inverting, even iteratively. And in fact, they're more complicated than the simple form. So what one needs is a way of taking a trial solution and moving it through the system. Now, most of these problems that occur in constraints and that are going to occur in the descriptions of the internet that I'll come to next involve networks which are at least like trees. Things branch off forever, and it takes a long time, even in the small world of today's internet, before an attempt to solve a problem by iterating out one path back through another path, by the fact that some of these things out here turn out to be the same. So the cavity strategy is to try to focus momentarily on a point and ask, What information reaches this point if I look at everything else in the system and for the moment remove this point? And you can solve a system of equations which works in to the clause that most directly affects this particular variable, and then you can take that information and pass it out to other clauses and do the whole thing again. So there's a principled strategy for working in very large systems and moving information in from the cavity around a particular point and updating your estimate of what happens at that point. And that is behind both belief propagation and survey propagation. So that's the end of what I want to say about that. That is, I think, the furthest point reached by physical methods. Some of the ideas are 50 years old and some of the ideas are still in flux. But I think we know a lot about how to optimize at any one point in time large complex systems by using these iteration of soft estimates methods. And finally, the cavity scheme, which in fact can be made rigorous under some fairly sensible assumptions, is a powerful way of pulling that all together. But what about time-dependent things? And what about situations like the internet, where not only is it big, but there's nothing in the culture of the internet that quite matches the conservative Hamiltonian, the notion that there's a well-defined energy that everybody cares about, that affects all systems. Now, in a material, if I move one atom, its motion will be felt by the atoms around it, and they will in fact react, and their reaction will get back to my atom, so that, let's assume I managed to stick my finger on the atom, I will feel the force of the other atoms back on it. That's not the culture of the internet. At least ideal, in a sort of idealism, the culture of the internet is selfish. People attempt to discover as well as possible what affects their, how best to get their immediate objective, and then they go and do it. Although there's certainly lots of altruism, and there are plenty of people who try to be good citizens on the internet, there also are people who try to be bad citizens because it amuses them. And there are things in between, people who just want to run a business and don't care who they get in the way of, like spammers. I don't think spammers are trying to bring the internet to its knees. They just think they'll make more money shortly before everybody else stops using email. So you have selfish imperatives. Now the internet is clearly one of these Barabasi networks by construction, because it's a federation of networks that have grown up over 30 years. Its engineering standards are set by a consensus of engineers, the Internet Engineering Task Force. Its economic incentives are set by the regulatory bodies of every country in the world in a very coherent and disorganized way. So how can we reflect this in a model? I'm going to sketch for you a really nice set of ideas that started with Christos Papadimitriou at Berkeley and have been evolved by his students and are now being studied by a number of people, that start by making selfishness, if you like, the core of a model for how the physical network, the links, the wires along which the packets flow, come about. So the first question you have to ask is, who pays for a network to come into existence? It's not God, it's not governments, with a few exceptions. It's individuals who choose to link themselves to other individuals, and they have to pay for a piece of wire from the phone company and the service that goes with it. So the first idea that Papadimitriou had is that one should come up with models in which you've assigned the cost of building the network to the individual participants in that network. And you come up with a plausible objective function, something like your ability to send email to all your friends, to gather information from all places in the world where things of interest to you are found. And each person is going to make decisions about adding links to their network, or selling or getting rid of links to the network and saving the money they've been spending, based only on whether it helps them to accomplish what they're setting out for. This is the extreme antithesis of the sort of the focus on energy that the physical method requires. In other words, I don't feel the other atoms pushing back when I make my decision on whether to purchase a link in the internet or not. I only get the immediate response. Over time, I may discover that there's a reaction to my actions, and I may change to a new strategy. So the global equilibrium is replaced by the Nash equilibrium, or I will argue something with even more limited information than the usual definition of a Nash equilibrium. Papadimitriou suggested that the first thing to think about is the price of anarchy, the price of selfishness. And that is the ratio between the sum of the Nash equilibria, sum of the costs of the the sum of the costs incurred by the individuals at a Nash equilibrium, a point in which nobody has any incentive to change, and the ratio of that to the social optimum, or the best solution in terms of minimizing the costs and achieving the best value for all people treated as a collective. Now, it is frequently the case in game theory that the social equilibrium is not a Nash equilibrium. There are lots of simple models that can show that. And that happens in a part of the phase space. I'll spare you the trivial question. The answer is TCP/IP is a Nash equilibrium for the present internet. And there's even papers to show it, but this was posed 10 years ago as a nice question. The model that I'm going to talk about was refined from Papadimitriou's ideas by one of his students. And what we've learned is that a bunch of things. The Nash equilibria span quite a range away from the global optimum. But in fact, the worst case focus in the original papers on the price of anarchy, the worst thing that would be stable and the best that you could do, is probably an inappropriate characterization, because under plausible assumptions, both the selfish equilibria and the global equilibria that you could find by searching with a single control strategy are quite sharply distributed. And their ratio is much closer, they're much closer to each other than the worst case analysis would suggest. So here's the model. Each link is purchased only once at a cost of A dollars or A euros, or 1 Austrian shilling if that still existed. Once purchased, everybody can travel in either direction across the link, so they're non-directional links. And each site makes decisions to purchase or get rid of links based on the cost of the links that they have to buy, plus the sum of all distances, and there are various models for distances. It's easiest to think about all distances being the number of hops you have to go over. But there are far more realistic models that people are starting to study using this kind of analysis. So if any distance, if a site is not connected, that distance is infinity, and so you want to avoid that. So this is a question of how to proceed with networks that are connected so that everybody buys no more links than they have to. And because they make their decisions asynchronously, they're not really able to care very much about optimizing the whole. They're just trying to do their own job as well as possible. The social cost, as I said, is the sum of the cost to all sites, and the price of anarchy is the ratio of the Nash equilibrium that you stop at in a particular decision process, a particular run of the simulations that we've done, to the social optimum. Now, there's some bounds on, there's a result for small costs of links, and there's a bound for large costs of links, but let me tell you a little bit about what happens. If the cost of a link is small enough The ideal situation is that every pair of members of this group, members of this network, has a link between them. If the links are cheap enough, obviously, you just buy all the links that you think you need, and pretty soon somebody would have purchased every possible link. This gets you to a situation where all distances are 1. And if the cost is small enough, that's obviously optimized the distance part of the problem. The other extreme is when the links are extremely expensive. Now, the best solution is a star. I think I've got pictures of that coming up. I'll spare you this, but you can just read it. Okay, thank you, Mr. Paperclip. You may go away. And I'm also, because of the impending possibility of going somewhere for a beer, I will return to that if anybody has a question. Okay, so if A is less than 2, the solution is a complete graph. If A is greater than 2, the solution is a star. One site purchases links, or links are purchased between one site and all the other sites. And the diameter of this network is 2. The star can reach everybody, and everybody can reach the star in 1 step, but all other distances are 2. That's a pretty good solution to the distance problem. But anything else, any solution that increased the number of sites 1 step apart instead of 2 steps apart would cost a lot more. So the answer is a star if the links are very expensive. But what actually happens in modeling this process of reaching these decisions, and a similar but not exactly this, but different in detail thing happens in modeling global optimization with finite temperatures, is that something more interesting than the complete graph and a lot more robust than a star tends to happen when you use greedy, selfish solution with limited information. Now, the practical problem in simulating Nash equilibria is that the decision process at each member of the network is not something that's extremely costly to simulate, because in this model, each site has to decide whether to add or remove n links. So he has 2 to the n situations to consider. If we took a more plausible set of possible decisions, that is, look at all the links you don't have and say, do I want to buy that link? Look at the links that you do have and say, do I still need that link? That's only n instead of 2 to the n. And so a more plausible model is that a finite set of moves. For this model, the simplest set of moves is adding or subtracting 1 link. And that's something that probably could be assessed by the individual owner of a site in the time that he has to make a decision before somebody else changes the situation around him. So I think that's a good model. We augmented it in a way that's a little bit more powerful and not significantly more expensive, and that is to consider getting rid of a link that you have and trading it for a link that you don't have. So the replacement move added to that. Allow that, and you get very good solutions. Typically, you get the global optimum when the global optimum is a Nash equilibrium, except in an intermediate range of moderate strength alpha, where you get these open stars. What's happened there is there's a core of 3 sites replacing the single site in the star, and every site makes a link to 2 of them. So the graph that I've drawn, there's also 2 bonds between the 3, or sometimes 3 bonds between the 3 and the center. It has diameter 2. You can get from any point to any other point in no more than 2 steps. Overall, the world has now spent twice as much money on links as it would have had if we'd built a star. But the payoff is we've got a far more robust system. You remember the discussion in the first talk about how in scale-free networks it's easy to attack their most connected points and blow it up into little disconnected pieces, which is arguably a powerful attack and needs to be needs to be defended against. I don't think we want networks for any engineered purpose that are as fragile as the star. And so one question that emerges is whether we need to devise elaborate strategies to force networks to go against their selfish imperatives and build in redundancy. In global optimization, I can get things like this by simply keeping the temperature finite, by allowing everybody some flexibility to occasionally spend a little extra money, purchase a few extra links. And the end result will be, and I think I've got a chart to show it, that there are always multiple paths between any pair of sites. In other words, a much more reliable system, a more redundant system which is reliable against local failures. It also happens when you have limited information, even under this strong kind of selfish model. And so one conclusion is very possibly one doesn't need to cook the mechanisms of the game in elaborate ways because the nature of real processes are that people will not play an ideal game, and as a result, that leaves you with more redundant and reliable systems. The second point is when the cost of a link exceeds the number of elements in this model for distances, number of sites in the network, it no longer is attractive to an individual to care about whether he's a neighbor of a star. He's happy to be just a few steps from the center of the universe, sites like Yahoo, or routers like the one in Washington at the NSA that all of the internet traffic passes through. And therefore, the system will be stable at trees with a moderate level of branching, which again separates out, it still has the single point of failure, but it separates the cost in a nicer way. What I'm trying to show in this picture, which is drawn from a more realistic study with more reasonable distances, is that the fraction of the graph, I'm comparing global optimization, done approximately, with Nash equilibrium, with selfish optimization, looking for exact Nash equilibria. And what we find is that, this is a cumulative distribution, that the upper curve is the selfish optimization, and what I'm plotting here is the two-core, the fraction of sites in the problem that have at least two neighbors, and therefore they're not leaves on the outside of a star. And the reason I'm doing that is as these graphs get larger, one can show that the sites that have a pair of neighbors will also, with high probability, have a pair of paths between any other site in that group. And therefore, they have achieved the redundancy that I was talking about. And what we see is that the global optimization preserves this robustness, this ability that all but this small fraction of the sites have a pair of neighbors, and therefore two ways to start the path between themselves and any other site. And even if we ask the harder question of do we have three neighbors, and therefore the chance of three independent paths between each pair of sites, this is a case where the selfish optimization now fails quite badly, and we're left with only one curve at a modest value of my strength, my cost per bond. So there are some interesting questions in the things that lead to robustness and redundancy in these strategies, in these models. The model's obviously a toy, but what I would like to suggest is that there are at least two different ways to achieve redundancy. One of them is through plan, through a consensus decision that everybody will manage themselves to include the redundancy of the whole as part of their selfish optimization. And something that I think is more plausible and more likely to work, which is normal human nature, imperfect information, and the finite time to make decisions, can actually form a kind of a temperature. Things are not perfectly optimized, and the less optimized solutions appear to give better overall network properties. Now, my interest, I said at the beginning that I'm involved in trying to measure, manage, and understand the edges of the network, comes from a couple of things. I started with a map of the internet. You probably couldn't read it well enough, but that map was a tree. That map was gathered by searching outwards from a single point and finding as much as possible the whole galaxy and keeping track of the path to all the other known points in the galaxy. Well, that gives you a tree. It only branches out. The internet is not a tree. The internet is a mesh. At the AS level, there are peering arrangements between different service providers that allow all sorts of messages to flow sideways without having to go through Washington, D.C., or in this particular case, the map was gathered in Oregon. The services that I think are going to transfer the internet into a different and more personal environment to live in are services like peer-to-peer delivery, well, today of music and movies, but of all sorts of information as they get more distributed for just reasons of efficiency. Delivery by Akamai of commercial content that is at a fee spread out to a carefully designed regular network, non-scale-free network of servers is also exploiting the edge, the links around the edge of the network. Our objective in Evergrow is to go out there and find those links because mapping exercises have begun to talk about the dark matter in the internet, but we're only just as a community beginning to really measure its dynamics, ask questions like wireless stuff. How is it affecting the density of connections at the edge of the internet? Those are all going to have an enormous influence on the properties of services that we deliver over information networks and the connectivity of content as it gets more finely distributed around the edge of the web in the next 5 or 10 years. So the implications that I take away for designing really interesting functions are the ones that I told you, that we can try as hard as we want to come up with mechanisms that make people behave, but the thing that most offends us is just the normal finiteness of information horizons, the finiteness of decision times, and the fact that it's all changing so fast that you can't block it for very long. Now, I said I would move to the Avogadro scale, and I actually, I am less a believer in that I have a whole lot to say to the Avogadro scale than I was a few months ago. I participated in a very interesting workshop at the Media Lab that Neil Gershenfeld ran, where he specifically said, we're going to talk about Avogadro-scale engineering. And a lot of interesting people came to that. And it became clear, at least my conclusion, was that nobody at the moment wants to do what I would think of as Avogadro-scale engineering comparable to tackling the web and tackling large information networks in all of their local complexity. What people presently want to do that involves 10 to the 21st molecules is make medicines on a large scale using cellular manufacturing processes. That's one product. So they want to make a product set of one, in quantities large enough to put in capsules and sell as a medicine. As an aside, quantum computing is also using very complicated machinery to answer one problem at a time, and then you think about solving the next problem. So both of these nanoscale and if you like, non-p-space limited approaches to things we might do in the future are at the moment focused on a single outcome. So they're not scale-free. They are also, and I think the biomedical context is a cultural force here. They're unwilling to accept the risk of a wide range of outcomes, a spectrum of outcomes, even in a single-scale environment, because what you're making is a pharmaceutical, you've got to get it right, and you're very nervous about making medicines that kill people, which eventually Darwinian pressures will eliminate from the process that you're trying to design. So there's a certain risk aversion in the early attempts to do Avogadro scale manufacturing, and as a result it's being engineered in a way that is not what you would call flexible manufacturing or what large-scale logistic problems are tackling today. So I don't think we need to worry about the Avogadro scale right now, and I think the problems at the billion to what comes after a billion? A trillion. And in the UK, I guess there are different words for all of that, but problems on the American to British billion scale will be with us and keep us quite occupied for the next couple of years. So let me stop there. Thanks. Ooh, I get my glass?
You do indeed.
Thank you. Do I have to answer questions for the glass?
Thank you.
Okay.
Okay, yes.
Have you considered in your network growing model the case where different nodes have different utility for their links? So dynamic heterogeneity
Yes.
manifests itself in heterogeneous networks?
There's a couple of, heterogeneity is obviously the first thing to do. The first place you put it in is in the distances. I mean, saying that all distances are one is obviously an oversimplification. And if you want to think about peer-to-peer services at the edge of the network, one way to do it is to come up with a chunk of the real network or a plausible model of the real network with delays, and then place your sites at spots in the real network and ask them to go find paths on the underlying network and share information to shorten those paths. That makes the distance problem far more realistic, and it's still an interest. We are learning a lot from tackling problems in that way. Second thing is to, well, there's two things that I would change in the individual incentives. The first is you might want to think that a link is a partnership between its two ends and the cost is shared. And I think you'd see immediately more rational decisions made, or I should say more group-favored decisions made that way. And then the second thing is the cost of making a link ought to have some relationship to the number of links already present at the destination site. And both of those are being factored in to models that people are playing with now.
Any more questions? I think everyone has had enough for today. Thank you very much indeed.